This article is about the science of measurement. For the study of weather, see meteorology. Metrology is the science of measurement. Metrology includes all theoretical and practical aspects of measurement. Metrology is defined by the International Bureau of Weights and Measures as the science of measurement, embracing both experimental and theoretical determinations at any level of uncertainty in any field of science and technology. The ontology and international vocabulary of metrology is maintained by the Joint Committee for Guides in Metrology, a group made up of 8 international organizations: BIPM, IEC, IFCC, ISO, IUPAC, IUPAP, OIML and ILAC. Metrology is a very broad field and may be divided into 3 basic activities, though there is considerable overlap between the activities. Definition of internationally accepted units of measurement. Realization of these units of measurement in practice. Application of chains of traceability linking measurements made in practice to reference standards. Metrology also has 3 basic subfields, all of which make use of the 3 basic activities, though in varying proportions. Scientific or fundamental metrology. Applied, technical or industrial metrology. Legal metrology. Scientific or fundamental metrology. Scientific and fundamental metrology concerns the establishment of quantity systems, units of measurement, the development of new measurement methods, realization of measurement standards and the transfer of traceability from these standards to users in society. The BIPM maintains a database of the metrological calibration and measurement capabilities of various institutes around the world. These institutes, whose activities are peer-reviewed, provide the top-level reference points for metrological traceability. In the area of measurement, the BIPM has identified 9 metrology areas including length, mass and time. Applied, technical or industrial metrology. Applied, technical or industrial metrology concerns the application of measurement science to manufacturing and other processes and their use in society, ensuring the suitability of measurement instruments, their calibration and quality control of measurements. Although the emphasis in this area of metrology is on the measurements themselves, traceability of the calibration of the measurement devices is necessary to ensure confidence in the measurements. Legal metrology. Legal metrology concerns activities which result from statutory requirements and concern measurement, units of measurement, measuring instruments and methods of measurement, and which are performed by competent bodies. Such statutory requirements might arise from, amongst others, the needs for protection of health, public safety, the environment, enabling taxation, protection of consumers and fair trade. The OIML was set up to assist in harmonizing such regulations across national boundaries to ensure that legal requirements do not inhibit trade. In Europe, WELMEC was established to promote cooperation on the field of legal metrology. Metrological traceability. A core concept in metrology is metrological traceability, defined by the Joint Committee for Guides in Metrology as property of a measurement result whereby the result can be related to a reference through a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. Metrological traceability permits comparison of measurements, whether the result is compared to the previous result in the same laboratory, a measurement result a year ago, or to the result of a measurement performed anywhere else in the world. Traceability is most often obtained by calibration, establishing the relation between the indication of a measuring instrument and the value of a measurement standard. These standards are usually coordinated by national metrological institutes. National Institute of Standards and Technology, National Physical Laboratory, UK, Physikalische Technische Bundesanstalt, etc. Traceability, accuracy, precision, systematic bias, evaluation of measurement uncertainty are critical parts of a quality management system. Society. Sufficiently correct measurements are essential to commerce. About 9 out of every 10 people working in metrology specialize in commercial measurement, most at the technician level. Correct measurements are beneficial to manufacturing, but other methods are available and sometimes are more appropriate. Metrology has thrived at the interface between science and manufacturing. Aerospace, commercial nuclear power, medicine, medical devices and semiconductors rely on metrology to translate theoretical science into mass-produced reality. The basic concepts of metrology appear simple on the surface, and metrology is rarely taught in a systematic manner above the technician level. Within most businesses, metrology core beliefs such as recording all setups and observations for possible future reference are opposed to the general business practice of minimizing record keeping to limit litigation effects. Applied metrology. Metrology laboratories are places where both metrology and calibration work are performed. Calibration laboratories generally specialize in calibration work only. Both metrology and calibration laboratories must isolate the work performed from influences that might affect the work. Temperature, humidity, vibration, electrical power supply, radiated energy and other influences are often controlled. Generally, it is the rate of change or instability that is more detrimental than whatever value prevails. Calibration technicians execute calibration work. In large organizations, the work is further divided into 3 groups. Alternatively, the technicians can be divided by major discipline areas: physical, dimensional, electrical, RF, microwave and so on. But the principles are the same regardless of the equipment. Metrology technicians perform investigation work in addition to calibrations. They also apply proven principles to known situations and evaluate unexpected or contradictory results. Specific education in metrology was formerly limited to sub-professional work. Most of the branches of the U.S. military train enlisted grade technicians to meet their specific needs. Large industrial organizations also develop people who demonstrate aptitude in testing functions. When this is combined with an engineering degree, it qualifies the person as a metrology engineer. Over the last 15 years, universities such as the University of North Carolina at Charlotte have created a specific curriculum in metrology engineering. In England, metrology was part of the 5th year of some undergraduate engineering programs. Metrologists are people who perform metrology work at and above the technician levels. The metrology and calibration work described above is always accompanied by documentation. The documentation can be divided into 2 types, one related to the task, and the other related to the administrative program. Task documentation includes calibration procedures and the collected data. Administrative program documentation includes equipment identification data, calibration certificates, calibration time interval information and as found, or out of tolerance, notifications. Administrative programs provide standardization of the metrology and calibration work and make it possible to independently verify that the work was performed. Generally, the administrative program is specific to the organization performing the work and addresses customer requirements. General administrative program specifications created by industry groups, such as the ANSZ 540 series, may also be covered in the administrative program. Other specifications created by the U.S. Food and Drug Administration, U.S. Federal Aviation Administration or other agencies would supplement or replace ANSZ 544 work performed in the domains. Often administrative programs can be as complicated and detailed as the measurement work itself. Standards. Standards are objects or ideas that are designated as being authoritative for some accepted reason. Whatever value they possess is useful for comparison to unknowns for the purpose of establishing or confirming an assigned value based on the standard. The design of this comparison process for measurements is metrology. The execution of measurement comparisons for the purpose of establishing the relationship between a standard and some other measuring devices. Calibration. The ideal standard is independently reproducible without uncertainty. This is what the creators of the meter-length standard were attempting to do in the 19th century when they defined a meter as 1/10,000,000th of the distance from the equator to one of the Earth's poles. It was later learned that the Earth's surface is an unreliable basis for a standard, as the Earth is not spherical and it is constantly changing in shape. But the special alloy meter bars that were created and accepted in that time period standardized international length measurement until the 1950s. Careful calibrations allow tolerances as small as 10 parts per million to be distributed and reproduced in metrology laboratories worldwide, regardless of whether the rest of the metric system was implemented and in spite of the shortfalls of the meter's original basis. Modern standards currently, 5 independent units of measure or internationally recognized: temperature interval, linear distance, electrical current, frequency and mass. Any measurement can be based on one or more of these measurement units. To supplement these 5, 2 units of angle measurement that are also independent are recognized. For example, Ohm's law is a widely known concept in electrical study. Of the 3 units of measure involved, only current is an independent unit. Voltage and resistance units are dependent on current units, as defined by Ohm's law. It is believed that each of independent units of measure will be defined in terms of the other 4 independent units eventually. Length and time are already connected this way. If an accurate time base is available, then a length standard can be reproduced without a meter bar artifact, using the known constant speed of light. Lesser known is the relationship between the luminance and current. The candela is defined in terms of the watt, which in turn is derived from the ampere. Non-commercial measurement details used to be academic curiosities. However, engineering, manufacturing and ordinary living now routinely challenge the limits of measurement. The development of standards follows the needs of technology. As a result, some units of measure have much more resolution than others. The second is reproducible to 1 part in 1014. As it became possible to measure time more precisely, solar time, believed to be a constant, proved to be very slightly irregular. This resulted in leap-second adjustments to keep UTC synchronized with solar time. The candela standard is difficult to recreate. An incandescent bulb design must be used as a secondary standard, a supplementary standard, a transfer standard. These special candela standard bulbs recreate the candela when a specific amount of current is applied. Luminance can only be reproduced to 5% of reading despite having sensors that have accuracies of plus or minus 50 parts per million precision. This is due to the standard not being accurately reproducible. Temperature is defined by agreed fixed points. These points are defined by the state changes of nearly pure materials, generally as they move from liquid to solid. Between these fixed points, standard platinum resistance thermometers, constructed in a specified manner, are used to interpolate temperature values. This mosaic of approaches produces measurement uncertainty which is not uniform over the entire range of temperature measurement. Temperature measurement is coordinated by the International Practical Temperature Scale, maintained by the BIPM. Industry-specific standards in addition to standards created by national and international standards organizations. Many large and small industrial companies also define metrology standards and procedures to meet their particular needs for technically and economically competitive manufacturing. These standards and procedures, while drawing in part upon the national and international standards, also address the issues of what specific instrument technology will be used to measure each quantity, how often each quantity will be measured, and which definition of each quantity will be used as the basis for accomplishing the process control that their manufacturing and product specifications require. Industrial metrology standards include dynamic control plans, also known as dimensional control plans, or DCPs, for their products. In industrial metrology, several issues beyond accuracy constrain the usability of metrology methods. These include the speed with which measurements can be accomplished on parts or surfaces in the process of manufacturing, which must match the TAKT time of the production line. The completeness with which the manufactured part can be measured, such as described in high-definition metrology. The ability of the measurement mechanism to operate reliably in a manufacturing plant environment, considering temperature, vibration, dust, and a host of other potential hostile factors. The ability of the measurement results, as they are presented, to be assimilated by the manufacturing operators or automation in time to effectively control the manufacturing process variables. The total financial cost of measuring each part. National standards. Every country maintains its own metrology system. United States. In the United States, the National Institute of Standards and Technology plays the dual role of maintaining and furthering both commercial and scientific metrology. NIST does not enforce measurement accuracy directly. The accuracy and traceability of commercial measurements is enforced per the laws of the individual states. Commercial measurement generally involves any material sold by any unit of measure. Some intuitive or obvious measurement is generally exempted, such as selling cloth on a cutting table that has a yardstick fastened to it. All counting-based transactions are generally exempt also. But each state has its own rules, responding to the accumulated concerns of the state residents. Commercial metrology is also known as weights and measures, and is essential to commerce of any kind above the pure barter level. Every state maintains its own weights and measures functionality with traceability to the national standards maintained by NIST. Large states further divide this effort by county, where a sealer or other appointee is responsible for the validity of most common commercial measurements, such as mass balances in grocery stores, and gasoline pump measurements of volume. The sealer's staff and agents make periodic inspections to verify compliance, maintaining the integrity of commercial measurements. Depending on the specific state, other state government agencies can be involved. For example, electricity watt-hour meters and water delivery flow meters are commonly monitored by the state's Public Utilities Commission, who enforces the measurement tolerances and traceability to NIST through the utility providers. Highway State Police and the State Highway Department generally run the commercial truck weight measurement programs for safety purposes and to minimize the damage to road surfaces that overloaded trucks cause. Nearly all states license weighmasters, weigh-mistresses, scale calibrators and other specialists involved in commercial measuring equipment maintenance. The term commercial metrology is also used to describe calibration laboratories that are not owned by the companies they serve. Scientific metrology addresses measurement phenomena not quantified in ordinary commerce, such as the testbed pictured at the beginning of the article. Calibration laboratories that serve scientific metrology are regulated as businesses only. They may choose to have their work accredited by voluntary certification organizations based on customer desires, but there is no requirement to do so. Irresolvable disputes involving scientific metrology are generally settled in the civil court systems. Some federal government entities like the Federal Communications Commission and the Environmental Protection Administration are considered to be the final authority in the domains rather than the NIST. Disputes involving only metrology issues with those organizations probably would not be heard in any courts.